Alright, hi guys, welcome to this particular video about those three questions from whichever day we're up to today, which I think is day 26. Okay, so the first question is this one, where you're asked to find the area for this particular function here. So between that function, the x-axis, x equals 0, which is the y-axis, and x equals 2 pi. Now you've got a graph, so the first hint I'm going to give you is look for some symmetry in that graph. Okay, and yeah, so that would be the one hint. The other hint would be that I think you need to be using some x-intercepts, or the intercepts where sine x minus cos x, okay, where that is equal to 0. In other words, where sine x is equal to cos x. Okay, and then you just use normal integration methods. Okay, so pause the video and have a go at that particular part now. Alright, so when I had a look at that graph, looking at the symmetry of it, I realized, well, I think there's one area we can get, and that is where this function's meeting this one, and then basically it would be two lots of that, as far as I could see. Okay, so if you're finding out then those points of intersection, which will be useful for finding that area, the initial area. So coming back to the actual graph, let me just bring that up. So this particular one here, so I was looking at this area here, and then looked at it and thought, well, this area that I've got here plus this area I've got here is just another one of these ones that I've got striped there. So if that's the case, then we can just get the area from this point here to this point here, okay, and then, as I say, double that to get the total area. So to get, okay, this point here and this one here, it's where the two graphs basically where they're equal. In other words, where sine x minus cos x is equal to 0. In other words, where sine x is equal to cos x. So if we go back to here, now from your trig work, you should know that one point would be pi over 4, and the other one would be 3 pi over 2. So they're going to be my limits on an integral. So I called the initial area I'm finding, I called that A1. Okay, and these are my limits, 3 pi over 2 and pi over 4 for sine x minus cos x dx. Okay, now if you then integrate, okay, that's going to be minus cos x minus sine x between those limits. Sorry, this is a bit laggy here, this interface I've got here. Just using a slightly different location to do this video. Alright, so substituting in and also using one of those special triangles, the one with the pi over 4 angle in it, you should end up with, after you've done the calculations here, of 4 over root 2. I'm going to let you confirm that for yourself. Okay, therefore the total area due to symmetry is 2 times that. or root 2 squared over root 2 times 4. Okay, and that's going to give a total of, what are we going to get, 4 root 2? Yep. Unit squared. Okay, so that's the first one. Alright guys, the second question then, what you're given is you're given this log statement that log of b base a over b is equal to 5, and you're asked to find the value of log base a over b, then b, the cube root of b, times the 4th root of a. Now, a couple of clues here. This log statement can be written in indice form, and that would be quite useful, because another clue about this one would be if I can get a here, this a in terms of b, then perhaps I can use the fact that this log statement, or the equivalent indice statement, I can then substitute for. Okay, so one hint, have a look at this in indice form and then try and get a as the subject of that. And then when you're figuring this out, look to substitute for a in terms of b. Alright, so pause the video, see if you can make something of that. Alright, so writing this log statement in indice form, I'm going to get a over b to the power of 5 is equal to b. So that would mean a to the power of 5 over b to the power of 5 equals b. So b to the power of 6 equals a to the power of 5. So a would equal b to the power of 6/5. Okay, so then looking at this log statement, we can say that this is equal to, well, first of all, I'm going to rewrite those roots as powers. So b to the power of 1/3 times a to the power of 1/4. Now we do need to also use one of the laws of logs. That's to split this up into 2 separate logs. So log AB is equal to log A plus log B. So splitting this up. And a second law of logs we're going to need to use is to move these powers to the front. So we're going to get 1/3 log base AB of B plus 1/4 log base AB of A. Now substituting what we've got for A equal to b to the power of 6/5 over here, okay, I'm going to get 1/3 times, well, that's equal to 5. We're given that as a initial statement, plus 1/4. Okay, and in place, so log base AB, A over B I should say, and A is equal to b to the power of 6/5. Okay. Okay. Well, this here is going to become 5/3. Now, what can we do with this here? Well, okay, I'm going to rewrite, okay, I'm going to put this power of, that number 1/4 back here. Okay, so that's 6/5, and that would be times 1/4 there. So it's going to be 5/3 plus log base A over B. Okay, and that will be B to the power of, what are we going to get? 6/20, which is going to become 3/10. Okay, and then we can move that power of, that intercept, the power to the front. So we're going to get 3/10 times log base A over B of B, and that will be 5/3 plus 3/10 times 5. Okay, so just squeeze it in here. So it's going to give 5/3 plus, okay, that's going to cancel down to, cancel common factor of 5 there, so we get plus 3/2. And if you add those two fractions, you end up with 19/6, which is the final answer. Okay, so the slightly tricky thing maybe, maybe putting this this quarter at the front here was not needed, and we could have instead simply substituted in place of A this B to the power of 6/5. So another way of setting that out, which may be slightly clearer, would be at this stage here, okay, log of A over B, and that, replace that A like that, and then that's all to the power of 1/4 there, instead of moving the quarter at the front and then having to move it back again. So that could be a little clearer. Alright, so that's that one done though. Okay, and moving on to the third one. Okay, so just going to pause the video here. Right, so guys, in the third question, you're given a written statement. It says, from all possible pairs of positive rational numbers. Now remember, a rational number is something that can be written as a fraction. So essentially, we're looking for two positive numbers that add up to 11. Find the pair that maximizes the product of the square of the first number and the cube of the second. So the first thing we need to do is to write that as some equations. So the first hint would be to do that, okay, and also to get some variables. Okay, so I've used, for example, calling the two numbers x, y. Okay, and we need to write a statement that says that these two numbers, these rational numbers, so we could say that x and y are an element of Q, which is the symbol for rational numbers. So they add up to 11, and then the square of x times the cube of y, that's what we're trying to maximize. So the only other clue I'd give you is that we can come up with an equation for that value in terms of one variable by using that first equation where the sum of these two is 11. So pause the video here, have a go. Right, so guys, welcome back. Okay, so what I did was say, well, x plus y must equal 11, and the sum value, I'm going to call it v, which is the square of the first number times the product, meaning times the cube of the second number. That's what we're trying to maximize. From this first statement, I actually made y the subject and got 11 minus x. Okay, so this value in terms of one variable then would be x squared and then 11 minus x cubed. That's what we're trying to maximize. So I thought about multiplying this out, and I thought, no, we could actually just use the product rule. Let's have a go at that. So dv over dx, using the product rule, 2x, then this bracket, plus 3 times that bracket to the power of 2, times the derivative of what's inside, which will be -1 times x squared. Okay, now this we want to find out for a maximum will equal 0 when, well, there were some common factors that I looked at here we can take out. We can take 11 minus x out, 11 minus x squared out as a common factor. Another common factor we can take out from these two parts here is x. So what would we get? So we're going to have 2 times 11 minus x. And what would this be? This will be minus 3x. Just double checking there. Yep, that looks okay to me. Alright, so when will that equal 0? Well, there's some possible answers here. We'd have 11 minus x is equal to 0, gives x equals 11. We could have also x is equal to 0 straight off. Now, if you have x is equal to 11, then y would be 0, and if x is equal to 0, then y is 11. If you substitute them into here, then you get a total value, okay, of 0 each time. So I don't think those two are going to be valid answers. Okay, the other answer we can get is when this is equal to 0. So we're going to get 22 minus 2x minus 3x is equal to 0. That's going to give 22 divided by 5 is equal to x. Okay, and from that you can then get the y value. So we've got 22 over 5 plus y equals 11. Okay, so 11 would be, well, let's just put 11 minus 22 over 5. So that's going to be 55 over 5 minus 22 over 5. So that's going to be 33 over 5. Okay, so that is the values, I think, that maximize that value that we're after. The only thing which I haven't done here is to prove that that does give a maximum. So what I did was I then used the first derivative test and drew up a little table. Okay, and then you can substitute x equals that 22 over 5 into your derivative, this one here. Okay, and then take a value slightly less than that, and something slightly more than that. At 22 over 5, the derivative is equal to 0, so that's a flat line. Now you can have a look at what are the values of the gradient before and after that 22 over 5. So I'm going to let you confirm that it does give a maximum. Alright, so guys, so that's it for that third question.